All right, so let us go back to the previous example in the last class. I have just written them down. I had the matrix A, I had computed the RREF of A, and then got column space of A, row space of A, which was column space of A transpose, null space of A, and null space of A transpose. Fine, which was same as the left null space. This was same as left null space. Fine. So I would like you to understand them somehow. Look at R4. What are the subsets of R4 from here? All right. So what are the subsets of here in R4? So to understand what they are, so again this is matrix is of 3 cross 4. So I've got F from R3 to R4. I am defining f of x is equal to Ax. Does it make sense? Or is this the function f from R4 to R3 and saying f of x is equal to Ax? Which one is the right one? How do I find out? So the idea to find out is look at the matrix and look at the matrix multiplication. So the matrix is given to be A is 3 cross 4. So I need to have x which is 4 cross 1. So this x, which is the element of the domain, has to be of size 4. Fine, but if I look at here, A is 3 cross 4 is fixed. This x is 3 cross 1. So this matrix multiplication does not make sense. Multiplication does not make sense. Fine. So what I wrote here was wrong. I cannot write this, but this is a meaningful object for us. All right. But we can also think of this, defining it differently. I can define f of x as x transpose A. Now x is 3 cross, so I can think of this as 1 cross 3. This is 3 cross 4. So I get a matrix which is 1 cross 4. So when I want to do calculation using rows, I can define things this way. Is that okay? So depending on whether you want to study things with respect to column vectors or row vectors, you can define it differently. There is no issue with that, and because of that all these notions have come: column space, row space, null space, and the left null space. Because of those all these ideas have come, and they are related also. So I would like you to understand them nicely. Fine. So this, if I look at column space of A, it is a subset of R3. What about the null space? You are looking at all x, y, z, so this is a subset of R4. This is again you are looking at x, y, z, w, 4 of them, so this is a subset of R4, and this is a subset of R3. Fine. Look at it nicely and understand it. Now let us look at the dimensions here. Now there is only one condition here, so the dimension of this space will be 3 minus 1, which will be 2. Fine. Look at this part. This is also a subset of R3. There are 2 linearly independent conditions, or there are 2 rows of the matrix that I am looking at. So I am looking at the null space, means I am looking at this one. So if I want to look at here, I am looking at x, y, z, 1, 0, 4, y is 0, 1, minus 3. I am looking at this set. This is the solution space here of null space. There are 2 pivots here. So the dimension of this space is 3 minus 2, which is 1. Fine. You can see that this plus this adds up to 3. Understand it. This is also you are looking at 4 minus 3 minus 1 of x, y, z is equal to 0 as such. Fine. Similarly, if I look at these two, here this corresponds to the matrix looking at 3 minus 2 minus 1, w is 0, 5 minus 3 Oh, I wrote u here in place of w. So, let me write it u here, all right, 0 and 1. So, I am looking at this system here, A is this and x, y, z and u, fine. So, again I have got 2 pivots in some sense here, you can see here. So, therefore, the dimension of this is 4 minus 2, which is 2. Here also there are 4. So, it is 4 minus 2, which is 2. So, this 2 and this 2 add, you get 4. So, the question is that is there a relationship between these ideas? That is one thing, fine. The other thing is that is there some relationship between column space of A and null space of A. So, the idea is to understand the relationship between these spaces one after the other. So, first we will try to understand the relationship between column space of A and null space of A. We will try to understand that, and that is called the rank nullity theorem. So, we will try to understand the rank nullity theorem, and then at the next stage we will try to understand something more, what are called orthogonality of all these spaces. So, I will have to go to what is called a dot product and then do it. So, first let us go to what is a column space and null space, what is the relationship between them. So, let us look what is called the rank nullity theorem. So, A is m cross n, we are starting with this. We know what is the rank of A, all right, rank of A plus dimension of null space of A is equal to n. What is n? The idea of this was we started with solving A x is equal to b, A was m cross n, x was n cross 1 and this was m cross 1. That is another way of understanding it, where which subspace is where. So, this n is number of unknowns, a number of variables that you are looking at, fine. Recall when we had looked at the system of linear equations, the main theorem there, if the rank was r, there were n minus r free variables. So, rank r implies r pivots, implied r basic variables, and therefore, I got n minus r free variables, fine, and therefore, I got n minus r ui's. Recall that there are ui's such that A times ui was 0, right. So, recall that part. So, I am just trying to prove that. There we got with an example, we could not prove it so well. So, I am trying to prove things now. Is that okay? So, let us do that proof of this theorem now. So, we are going to prove this theorem, that rank of A plus the dimension of null space of A, this dimension, this word dimension of null space is called nullity of A, all right. And generally we write it as rho of A plus nu of A is n. So, this is for rank of A, this is for dimension of null space of A, is that okay? And n is whatever the domain space or number of unknowns, fine. So, let us use whatever theory we have built up to understand it. So, proof. So, assume dimension of null space of A is some k, fine. So, this implies, all right, null space of A has a basis consisting of k vectors, all right. So, important, null space of A has a basis consisting of k vectors. Let they be u1, u2, uk, all right. So, I am saying that they are a basis, it means they are linearly independent and a span, is that okay? Both the things are true. So, what we are saying is A of ui is 0 for 1 less than equal to I less than equal to k, fine. Now, what we had learnt was that, so now if I look at this set U1, U2, UK, this is a linearly independent subset of Rn. That is very important. Ui's are elements of Rn, I am multiplying A. Alright, Ui's are supposed to come here because I am looking at Ax. So, this is n cross 1. So, what we know is that U1 to UK, they are subset of Rn, they are linearly independent set. Since it is a linearly independent set, so what does that imply? It implies by the theorem that I can extend it to get a basis. So, there was this theorem which said that every linearly independent set in a finite dimensional vector space can be extended to form a basis. Fine. So, here I have got U1 to UK, a linearly independent set in Rn implies extend it to get U1, U2, UK and then UK plus 1, UK plus 2 till Un as a basis of Rn. Is that okay? So, I can get it as a basis of Rn, that is more important. This part is for null space of A and overall. Is that okay? So, I have got a basis for this. I want to claim. So, claim. So, look at things that what is range of A? Range of A was nothing but column space of A. How do I get a column space of A? Column space of A, I am claiming that this is nothing but linear span of the vectors A of U1, A of U2, A of Un. I am saying this. Why I am saying this? Because if I want to look at column space of A, by definition column space of A is Ax, x belonging to Rn. Is that okay? Now, what we know is that U1 to Un is a basis. So, since U1 to Un, this is a basis of Rn, x is nothing but any x. So, any x will look like some alpha 1 U1 plus alpha 2 U2 plus alpha n Un. So, any x belongs to the linear span of U1 to Un, is not it? Fine. So, again recall what is a basis? Basis is linearly independent set and it spans. So, it is able to span. So, if I take any element x belonging to Rn, I am able to get x using some linear combination. So, there are these scalars alpha 1 to alpha n, I do not know what they are, but they are there. Fine. So, now if I multiply with A, so A of x is nothing but alpha 1 times A of U1 plus alpha 2 times A of U2 plus alpha n times A of Un. So, basically what I am saying is that Ax is a linear combination of A of U1 till A of Un. Is that okay? So, each of them is being represented as such. Fine. So, any element Ax, if I look at here, then this is a subset of, all right. This is a subset of linear span of A of U1 till A of Un. Is that okay? And the linear span of U1 to Un is the whole of Rn. So, I am looking at only this part. There is nothing wrong, everything is okay. So, this part is equal to this, because any Ax is in the linear span of A of U1 to A of Un. Fine. And vice versa, you can prove it yourself, because linear independence will imply that they are invertible and things like that. I can get a standard basis U1 to En using these and vice versa. Fine. So, I have got this. Now, let us look at this, what is column space of A. So, I can rewrite it. Column space of A is linear span of what is A of U1? A of u1 is 0, A of u2 is also 0 and 0 till A of uk, because u1 to uk, u1, u2, uk, they were elements of null space of A. They were basis of this. So, A times those ui's are 0, the rest I do not know what they are. So, they will remain as it is. Fine. So, they will remain as it is. So, therefore, what I see is that column space is nothing but is generated by linear span of A of uk plus 1 till A of un. How many vectors are in this set? N minus k plus 1 which is n minus k. All right. So, I would like you to now understand again what is n. N is the number of elements in Rn, a basis of Rn. So, those were the basis elements for me. So, this is what it is. Fine. Out of that, k of them are coming to null space. The rest of them, they are coming to the column space. Is that okay? So, somehow I have to prove, I can see that column space of A is generated by these vectors, because it is the linear span of these. I will have to prove that dimension of, or these vectors are linearly independent. So, to imply that dimension is there. So, need to prove, need to show the vector, show this set A of uk plus 1 till A of un is a linearly independent set. Fine. If I can show that, if yes, this will imply that column space of A is generated or spanned by this as spanned by T, and T is linearly independent, implies T is a basis of column space of A, and this will imply that dimension of column space of A is equal to number of elements in T, which we just saw, it was n minus k. Fine. And this will imply that k plus n minus k is n, k for dimension of null space of A and this for column space of A. So, dimension of null space of A and column space of A gives you this, and this completes the proof. Fine. So, I just have to show that this set is linearly independent. So, let us try to prove that this set is indeed linearly independent. So, if I prove that something is linearly independent, what am I supposed to look at? I am supposed to form a system of linear equation in certain unknowns. So, consider the system, consider the linear system C1 times A of uk plus 1 plus C2 times A of uk plus 2 plus so on C of n minus k A of un is equal to 0. In the unknowns C1, C2, Cn minus k, to show it has only the trivial solution, C1 is equal to 0 is equal to C2 is equal to Cn minus k. I have to show this, only the trivial solution. All right. So, let us try to do that. So, what we see here is that if I look at this part, fine, it is C. So, I am trying to solve a system which is C1 AU k plus 1 C2 and so on. Now, A is a matrix. So, I can take out A on the left. So, I can rewrite it as A times C1 U k plus 1 plus C2 U k plus 2 plus C n minus k U of n is equal to 0. Fine. I have just taken out A on the left, matrix multiplication. So, I have got this. Now, this part tells me that this vector implies this vector C1 u k plus 1 plus so on till Cn minus k u n, this belongs to null space of A. Is that okay? This is important. So, it says that this part, this vector, whatever that vector is, this vector is a linear combination of u k plus 1 to u n, but it is an element of null space. Now, since it is a base, it is an element of null space, all right. So, it will imply that I can write this vector C1 u k plus 1 plus C2 u k plus 2 plus Cn minus k u n. This is an element of null space of A. Null space of A has a basis. What is the basis? Its basis is u1 to uk. So, I can express this vector as linear combination here. So, I can write this vector whatever that is as some alpha 1 u1 plus alpha 2 u2 plus alpha k uk. Is that okay? Understand? The left hand side is an element of, fine, somewhere, I do not know where it is, but at the same time we have shown that A times that is 0. So, therefore, this vector belongs to the null space. Since this belongs to the null space, I can express it in terms of the basis of the null space. So, I can write like this. But this is equivalent to looking at, just look at it, alpha 1 u1 plus alpha 2 u2 plus alpha k uk plus minus 1 times C1 or minus C1 times uk plus 1 plus minus C2 times uk plus 2 plus minus Cn minus k times un is 0. Fine. So, the system of equation that I had, which I had started with, which was related with the idea of C1a uk plus 1 plus C2a uk plus 2 plus Cn minus k a un 0. This system of equation that I had started with has led me to a new system of equation which has all the n variables. So, it has got the vectors u1, u2, uk, uk plus 1, uk plus 2 un. So, I have got n vectors and I am looking at a system of equation in all those n vectors. Now, what are those vectors? These vectors are nothing but a basis of Rn, all right. So, u1 to un, this is a basis of Rn, and therefore, this has a unique solution which is given by alpha 1 is 0 is equal to alpha k is equal to minus C1 minus C2 minus C n minus k, and therefore, I get that each of these Ci's has to be 0. Fine. So, understand here that from this system we went to this system which was about a basis of Rn, all right. This was the basis of Rn which was there, and for the basis of Rn we need that each of these linear combination, each of these coefficients must be 0. So, the alpha i's are 0, Ci's are 0, therefore, the Ci's are 0 here, therefore, these vectors that I am looking at, they are linearly independent, and this is what we wanted to prove, that this set has to be linearly independent. We have done that, and since we have done that, therefore, the answer is yes. Once the answer is yes, so columns of A are generated by T and T is linearly independent. We have already shown it now. So, that T is a basis and therefore, this is this, and we have the result with us. Is that okay? Fine. Thank you.